as I understand it, this is a precursor to a more formal presentation elsewhere. Is that correct, Ivan?
Yeah, that's true, Jim. At Penn State.
Come forward.
Penn State.
The Lion's Lair.
The Lion's Lair.
Yeah, an abstract I put in on this topic was accepted by the reviewers. I guess that didn't include Michael Mann. And they were rather interested, and we were actually asked to put in an extended abstract, and I added some new hypothesis that I'm also going to introduce tonight, as well as the water hypothesis as a source of warming. I think it's important to understand that I'm talking about short-term variation. I'm not talking about long-term climate change, which occurs naturally as a result of geological factors. You were talking about that earlier. That's not my topic. My topic is to understand, for example, why the temperature has increased somewhat since 1960. And is that because of carbon dioxide? It's been increasing. There's a correlation, a rough one, not that accurate, or not. And it's important to know, I think, because if we're going to spend huge sums of money and resources, assuming that carbon dioxide is the cause of some problem, we may be wasting our money entirely. And I think there's a lack of certainty about the causation, to get rid of this flaming thing. So I've got two topics here to introduce. Now, atmospheric turbulence is something that I'm introducing as a new concept for climate. Water vapour, and I put these up as falsifiable reasons. Things we can do experiments on, test them and find out if I'm correct or not. I spent this afternoon flying a drone in my backyard, which is fitted with meteorological equipment, because on Sunday, well, tonight I'm going to the airport to meet my colleague from Bosnia, Migdat Hodzic, an electrical engineer, and we're going to Darwin on Sunday to join the AMOS IXMO conference. That's to do with oceans and atmosphere, where I'll be presenting a poster, or we'll be presenting two posters. And after that, we're driving to the Ord River. My brother's flying up from Perth to do the driving, because I can't be trusted anymore to do that. And we're going to take meteorological observations on gradients from the area that's irrigated to the nearby land that I assume will be dry. If it rains while we're up there, that'll be a problem. But it is the dry season. And anyway, it's fun learning to fly this drone. It's an amazing thing. I almost thought of bringing it tonight. So I'm asking the question, are the IPCC's models gambling with uncertainty? They're gambling with a lot of the world's resources. And what are the odds that they've actually picked a winner? I know some of the people here tonight think that they're very, very large, negatively speaking. I will touch on windmills. I also touch on irrigation tonight. I'm making a declaration. I'm not a skeptic regarding warming or temperature variation, at least in the short term. I mean, it happens every day. It happens from year to year. It happens during the 20th century. We saw cooling and warming periods. While CO2 is increasing all the time. But I want to know why and how. I also know that we humans can change the local climate by shading and water. This is just a matter of scale. Everyone who lives in the bush knows that trees around the house and a bit of lawn with water on them can make the living conditions much better. So we can affect a local climate. I'm not convinced that the focus on CO2 as the major cause of warming is valid. I'm challenging that. But if alternative causes are shown eventually to be invalid, only then can I agree that CO2 is the main culprit. Will I live long enough? I'm not sure. If you look at the projected causes of warning, this is the IPCC's model. Carbon dioxide contributing about 1.5 watts of forcing by its presence in the atmosphere, which would be increasing but at a logarithmic rate. Look at all these other things that are also contributing. I mean, this in itself should be give pause to governments spending so much money just on energy, because there are so many of these other causes. We have the reflective aerosols and aerosols, land use, acting in the opposite direction. And we have the change due to the sun itself, changes or variation in the amount of solar energy. And very important are the feedbacks, because CO2 has a certain effect. It's then said to warm the atmosphere to a certain extent, so it can contain more water, so you get a positive feedback. And that multiplies the effect of carbon dioxide, according to IPCC, by a significant factor, 2 to 3 times. So that water is very important from that point of view. Clouds are also very important in this. I haven't looked much at clouds, but I intend to include them in my regional models that I'm working on, using very simple programmable calculator logic to do this. I want to also make a summary of my talk. I'm giving an action revision. I call it, I'm very keen on the idea of action. It's a physical property, effectively has the dimensions of mass times radius times velocity. It looks like angular momentum, but it's a scalar property. It's what we see. When a planet is orbiting the sun, it has a certain amount of action. Satellites, anticyclones, cyclones have a certain amount of action because effectively they're rotating and they've got a radius and a velocity at which they're moving. So action is the property that you can actually estimate. Key issues, there's a lack of testable hypotheses. As Karl Popper would recommend. One gets the sense that a lot of the climate research these days is getting very repetitious, and they're not really testing hypotheses at all. They're just gathering more data, hoping that somehow or other the answer will pop out about what's involved. Karl Popper calls that process induction, and he says it doesn't exist. That's not the way science progresses. Science progresses through imagination, proposing hypotheses which can be tested. The better the hypothesis, the more rigorously it can be tested. That must be a quantitative procedure. So is the CO2 increase a cause of warming, or at least in part a result? This is a valid question. We know going back to the Ice Ages that a would-be American president proposed that carbon dioxide was causing the warming after the Ice Age. But the evidence is contrary to that. It looks as though the CO2 increase follows the warming. So where is the empirical evidence that CO2 is the main cause? This is a problem I have. Measurements are done in the lab. They measure how CO2 can absorb radiation. they can devise a mathematical model on that basis. But you do expect to have something to measure at the end of it that will tell you if your model is correct. There's also great uncertainty regarding the climate sensitivity. If the amount of CO2 doubles, how much forcing will that cause? And then that can be calculated. And then how much will the temperature change? So the climate sensitivity is the increase in temperature, the parameter they normally use for a doubling of CO2. And you get a very broad range of numbers according to different scientists or groups that calculate that. I think there's also a neglect of other possible causes of warming. And this is what my activity is about, suggesting that maybe it's not CO2. I think they stick to CO2 because they can't think of anything else. But I can think of something. I can think of something else. I can think of at least two things I'm going to talk about tonight. I'm talking about water vapour from irrigation, and I'm also talking about turbulent heating from surface friction. I think that this may be a variable that goes with modern civilization. Building cities, putting up windmills, and so on. Then I want to shortly make concluding arguments regarding mismanagement of climate variation. I have to go to the airport to meet my colleague who's arriving tonight at 11 p.m. on Emirates to take him back to his hotel. So I won't be able to go to the coffee club. I've shown this diagram before to some of you, and it shows the outgoing long-wave radiation. This is the radiation leaving the Earth in the infrared and microwave range from different geographical areas of the Earth. Of course, from the poles, you don't expect to see too much radiation emitted. It's so cold, particularly the Antarctic. The Arctic is somewhat warmer these days. But if you look at this diagram, you see that land areas, which are arid or semi-arid, Sahara, Arabia, India, Pakistan, Afghanistan, Gobi Desert, Chilean Desert. These are the areas where heat is leaving the Earth to a much greater extent. So what's the reason for that? If you like, these are cooling vents for the Earth. They tend to be hot places, but that's not the reason that they're pushing radiation out to space. The reason they're pushing it out to space is there's no water in those regions. No water in those regions. Of course, that's where we want to irrigate. If you go to the Middle East now, they're using deep groundwater to grow their crops. Jordan, places like this, grow their own food now from deep groundwater. This is new water that's never been allowed to evaporate into the atmosphere before. And the amount of water has increased by 4% over what would fall on land naturally. So that's a significant difference in the amount of water that's now applied to dry land. The drier it is, the greater the warming effect of that water will become. So if you look at, I think I'll go back to my pointer. If you look at the diagram, you'll see that the equatorial regions have diminished amount of radiation going to space. Why is that? Well, the reason is that that's a moist region and the atmosphere is very elevated and very cold as a result. And there's lots of cloud, so lots of reflection. The surface temperature is hot. The tropical areas, so it's not the decrease in radiation from the surface, it's the absorption of that radiation in that region. And you actually see a dip in the amount of heat going to space in the equatorial region. And you can put that down to water vapor and water in clouds as being the cause. What else did I want to say here? I think this diagram needs to be studied at length, but I never see it being discussed in the climate literature. I had to go to Wikipedia to actually drag this one out. And there's a clever group somewhere in the US that plotted all this data. The data is from NOAA, there's nothing wrong with it. The Earth's temperature, the Earth's emission on average is about 10 microns in wavelength. South Pole is longer, colder. Of course, the Sun is half a micron. Venus is about 4 microns in its emission. So there's quite a lot goes into those factors. I've already said that. Said that too. The areas here over the ocean are the descending Hadley cells. When the air goes up near the equator, it gets very cold and dehydrated. So when that air plunges down to the surface again, towards the poles, as part of the Hadley cells, it's very dry. And it's heating as it falls, high pressure. And as a consequence, more radiation goes to space. So the logic of this, I think, is all good. I agree with it. So it's not a result of a warmer surface temperature when you get more radiation going to space. It's really a result of water. Looking at the spectrum, this is the spectrum from the Earth's surface with the peak at 10 microns. Carbon dioxide absorbs in this zone. This is what they call the 667 centimetres to the -1 zone. That indicates the number of waves per centimetre. Water absorbs right through this region and also down here. And it overlaps with the CO2. Ozone is here. Now what this means is that the radiation from CO2 that's going to space is being emitted at a high altitude because there's so much there is enough CO2 in the atmosphere to absorb all the radiation up to kilometres of height. The same applies to water, but when you get to about 5 kilometres, the amount of water in the atmosphere diminishes, and therefore its ability to absorb radiation, an earthquake, its ability to absorb radiation diminishes faster than it does for carbon dioxide, because CO2 has the same concentration, relatively speaking, right to the top of the atmosphere, 0.04% parts per million vapour. So you've got absorption by water, but you've also got emission by water. This is the amount that's absorbed, but water will also emit to space, particularly in the longer wavelengths, in the microwave spectrum. So, anything more I want to say? Water has this very broad range. CO2 is emitting from very high, and this is at different latitudes, tropical, mid-latitude summer, mid-latitude winter. You have different spectra involved. But at all of these you'll see the carbon dioxide absorption. But this doesn't change if you add extra CO2 to the atmosphere. It stays more or less the same. What the IPCC is pushing is the idea that high in the atmosphere, if you double the CO2, the concentration will be higher up. And as a consequence, the absorption band will broaden a little. So a little extra radiation will be trapped by carbon dioxide. And the little extra we're talking about is the difference between here 375 and 750. It's the difference between this thick line and this dotted line. So this is supposed to be contributing the huge effect of carbon dioxide. This just very marginal difference. And it works out at a couple of watts per square metre when you calculate it, because the main absorption band is much stronger than that. But it doesn't change in height. You can see from the diagram that it's pretty much the same. There's a little difference. In fact, it seems to even increase that a bit. So you're just talking about these little areas. Now this is from laboratory calculations. It's not from actual observation. So I'm having a bit of difficulty reading this. Can I go over here? Yeah, this is better.
Follow you.
So you get these edge effects. I've already said most of this. But there's no satellite evidence for this. A group in England tried to get satellite evidence. They thought they had it, but they had to retract it because they're comparing 1975, I think, with 1997 and then 2003. But they've gone quiet. They're not publishing anything more on it. When it was first found, that it was greeted very enthusiastically by the climate centres, because it seemed to be proof that carbon dioxide was doing something. They thought they saw this little edge effect, but no one says that anymore. So it actually fails that hypothesis test. You don't seem to be able to see much difference in the spectrum. I've also got another suggestion to make. Heat is heat. If CO2 absorbs a little bit more on these edge effects, it will be hotter in its vibration. It will collide with other molecules, water in particular, and transfer that energy into rotation and translational energy. So why wouldn't water then just emit that little extra heat to space? Why can't water be a backstop for that purpose? I haven't discussed this yet. I'll do that next week in Darwin, but I would be interested to find out if anyone can react to that. Because after all, energy is a transferable currency. You can bank it, you can draw it out at different wavelengths. Why not? Now, the water, so if water's doing it, we should be able to see that from satellites. So that's a test of the hypothesis that I'm putting. That's my aim in all of this, to come up with tests for the hypothesis, which, as I said before, I think we lack. Many of you have seen these. This is the satellite temperature increase, showing about, this is on March this year, showing about 0.34 degrees variation from the mean value. So there seems to be a trend there. During the El Niños, you see the peaks, one here, 1998, a particularly strong one. And the global atmospheric carbon dioxide is, as measured at Mauna Loa, is increasing seasonally. In summer, it seems to be lower. I think that's because it's summer, there's more water vapour in the atmosphere, and that forces the carbon dioxide higher. Because water can become 10% of the atmosphere. And if you're going to maintain 1 atmosphere pressure at the surface, that means the other gases have got to go higher. So that would, and so that their concentration to be steeper. So that would apply to CO2. That would explain why it falls in summer. And here again, water is the key factor. Water is, and what they've said is that that's because photosynthesis occurs mainly in summer in the northern hemisphere, and respiration occurs in winter. Well, I'm a biologist. I don't understand the logic of that. Plant material breaks down when it's warmest. So it's not going to wait for winter to break down. If it falls in winter, it will be mainly degraded the following summer, not in winter. So that's a hypothesis that they claim is shown by that, but I don't agree with it. What have I done? Next. And this is the annual carbon dioxide growth. It's, despite all the activity, there's not much sign that the amount of CO2 increase is diminishing.
Straight line from 1975.
Yeah, that's right. Well, look, I mean, look at this year, it's very low. What was happening there? I think these seem to be periods of, well, I'm not going to analyse them. And this is the temperature increase, mean temperature over land and ocean. And this is the satellite temperature increase again. And there's a difference between the northern and the southern hemisphere. The northern hemisphere temperatures increased about twice as much as in the southern hemisphere. We were discussing that, don't worry about that. Carbon dioxide released from water as temperature rises. We know that happens. If I refer to the fact that your beer loses its carbon dioxide as it warms up, so you need to drink it quickly to prevent that happening. And it's a very substantial difference in the solubility. It's a significant factor. And natural recycling also consumes half of the fossil carbon dioxide generated. So we only see the increase in the atmosphere is only about half as much as the fossil fuels that are burned. But there's an order of magnitude more carbon dioxide being released and reabsorbed as part of natural processes. So it becomes a question as to what we're actually looking at when we see that increase. If, for example, the temperature is rising from other causes, that may be because there's more CO2 in the atmosphere. This is something I'm looking at the moment, in particular looking at what's known as the Henry Lawes constant. And this varies by a significant factor, but it's not enough to explain the increase in carbon dioxide, just as a question of the solubility in water. Possibly the release of carbon compounds in the ocean might be marginally increased as it warms up a bit, and that could be a source of a lot of this carbon dioxide, not fossil fuels. I think this is still an open question. So when you see that curve, you don't have to assume that it's a matter of fossil fuels, because it's just the balance between what's being carbon that's being oxidized and carbon that's being reduced or absorbed into the system. So, but I also raise the question, are we already addicted to higher carbon dioxide? Carbon dioxide, there should be more of it, some say.
Signature line.
C3 crops like wheat and rice yield more as carbon dioxide increases, because they work at a suboptimal carbon dioxide concentration in the evolutionary scale. They evolved when there was more carbon dioxide was around. So higher carbon dioxide means stomates close. On the bottom of the leaves you have these little openings that let in carbon dioxide and oxygen and release water. And the more they are open, the more water you need to grow the crop. But if the CO2 increases, they close. And consequently, you get better water use efficiency. So I think that plans to capture CO2 if someone comes up with a mechanism of pulling it out of the air, will cause revolution. Because that will mean we'll starve, because we won't be growing enough food, because we become addicted to higher CO2. That's already happening.
It'll just partition back out of the oceans. When they do that, it'll just partition back out of the oceans.
Well, of course it will.
Take up the slack. It's futile.
But they talk about carbon capture technology, and when Kevin Rudd promoted that, my letter was headlined in the Australian, pointing out that this is totally against the second law of thermodynamics and the amount of energy you need to do that. Some geologists still talk about it, putting it down wells. You can do it on a very small scale, but really you're mortgaging the future if you do that, because sooner or later it's going to come out. And if it really is a problem, not a good thing. So I think that a risk management and cost-benefit analysis needs to be paramount. You could call it the Lombo approach. We really need to establish priorities in this area. And all this activity to do with energy may well be misplaced and won't make any difference. We'll have windmills, we'll have solar cells. I'm not against solar, I think it's great. But I'm not too happy about windmills because I think they may be contributing to the problem. This is the trend burst diagram. It indicates heat flows on the Earth. This is the amount coming from the sun. A lot is reflected. Some of it's absorbed by the surface and a lot more is absorbed by the atmosphere. And then the energy going out has to match, has to be equal roughly. Otherwise the Earth would be getting hotter or getting cooler if they don't match. The ways heat leaves the Earth surface are by evapotranspiration, which is then released in the atmosphere, that heat. Also direct surface radiation, some of which is absorbed in the atmosphere, but some of it goes through to space. And to balance that, we have what's called the downwelling radiation. I don't think John is here, is he? Now, John is very much against this idea on the second law of thermodynamics, that you can't have a colder atmosphere heating the surface. But that seems to be what this is saying. This downwelling radiation somehow or other is much warmer than it would be if we didn't have an atmosphere. Recently, so that's so doesn't this contravene the second law? That's another reason I'm doubtful about that sort of model. I have shown this diagram before. I'm not going to dwell on it. As you know, I've been very keen on developing my own physical models, and this is just an example. I'm not asking you to understand it, but you get a temperature gradient, you get a pressure gradient with height, you get energy exchange, CO2 and water absorb radiation, but they then heat up the nitrogen, the oxygen and the argon. So the heat is distributed very broadly. The amount of water in the system is not that great. And you can come up with energy budgets. So again, I'm not going to go into those today. But I was thinking earlier this year how to solve this problem. How could the surface be warmer than the atmosphere? And I've come up with a new hypothesis about the energy that's coming from the Earth's surface being absorbed in the air and then generating anticyclones and cyclones. Normally, the climate modelers only count the constant pressure heat capacity of the air, as you can measure in the laboratory. But the hypothesis I'm making is that the rotating masses of air contain a lot of potential energy in their angular momentum. And to my surprise, when I calculated it using an approach I've got, it's 10 times as much as the actual heat capacity measured in the laboratory. So this means there's a huge potential heat absorbing process doing work on the atmosphere, getting it rotating, affected by the Coriolis effect, which has not been considered in the past. Wes, you haven't heard of that before, have you? Maybe he has. Wes is, I know that he's very much involved in looking at the water from volcanic eruptions, and I accept that that's a very important factor that does enter into what I'm talking about. And then the surface is heated by turbulent friction. If you have a mass of air or flywheel, think of it as a flywheel, in friction with the surface, its velocity will decrease as you reach the surface. That means that the energy that was contained in it is continually being transferred and emitted and radiated locally. So this seems to overcome this problem about the second law of thermodynamics. And I'm quite excited about this hypothesis because it may be telling us something that we really need to know if we're going to understand climate change. It does mean there's a lot more heat capacity in the atmosphere than we ever thought. Therefore, the climate sensitivity to greenhouse effects may be drastically diminished because it will just take so much extra heat to get the atmosphere moving. Of course, it's on a continuous basis, so there's energy always coming in through these processes spread over the Earth's surface. But it's also through friction being released, particularly into the lower environment where most of the friction occurs, because that's where most of the air is. So I'm trying this idea out on this audience tonight, just to see if someone might be able to see the logic of what I'm saying.
Absolutely.
Okay, good. Thank you. So I would say that the downwelling radiation is just turbulent surface heating. If you go out with a radiometer, you can measure it. So one of the things I'm going to do with the drone, did I talk about the drone earlier? Is put radiometers on it. And it itself will create a bit of turbulence, but we'll have to work out some way of doing that. But if we can put up obstructions and causing turbulence, we should be able to measure the extra radiation that will come from that. So it won't.
You could put a hurricane in the calorimeter, that'll help.
That's right, yeah, exactly. Yeah. Well, the thing about tropical cyclones, if you look at the theory of them, is that the kinetic energy is minor. Most of the energy in a cyclone is in the water vapour that comes from the ocean. So you have a warm ocean. This is why you get tropical cyclones over a warm ocean. Warm water, evaporation, cyclone motion, and particularly if it shrinks in size, it's got this extra energy, and this what I call vortical energy will keep it going. The kinetic energy is negligible in a cyclone. Wind speed, of course, can get very high, not in the centre, but near the centre. But even then, the amount of kinetic energy is not very great. So as the potential energy of the rotational motion is taken into that system, that's how you do the destructive damage. So it's really through coming here to 5Doc that I've been able to develop these ideas, because I don't seem to be able to do it at the university. No one really wants to discuss anything these days. So get rid of this idea of the downwelling radiation. Talk about the flywheel effect, and you can see what I'm talking about. That's good. I think you can too. That's good. So I'm going to be interested to see how that will be handled in Darwin and in Penn State. Where am I coming from? I mean, this is not just guessing. This is good physics. If you're looking at molecules in air, they vibrate, they rotate, they translate. And I also say they move in vortices. Every one of those adds to the entropy of those molecules. And it turns out that the vortical entropy is the greatest by far. And that's because of the huge distances involved. You're talking about 500 kilometres. That's 5 by 10 to the 7 centimetres. Molecules moving in air are moving separated by about 10 to the minus 7 centimetres. So you've got a difference in the radius of motion or action of about 10 to the power 14. And to my surprise, when I wrote a simple program to calculate that, I found out it was 10 times greater than the actual heat capacity as measured in the laboratory. So that's simply not included in any of the current climate models. So this is for vibration. These are my equations. If anyone is interested, I'll send them to you. But from that I can get the vibrational entropic energy, and it's quite small. Even for carbon dioxide, it's very small. I can get rotation, molecule rotating, in this case nitrogen or oxygen. And these are the equations I use there. This is for three-dimensional molecules like water. Translation, that's the separation between the molecules and their rotating motion. And that adds to the action and it adds to the entropy. The entropy is a logarithmic function of the action. I've just had a paper published in a journal called Entropy of all things. It's taken me 10 years to get this paper published because they can't find reviewers. Oh. I even went to London to see the editor of the Royal Society Proceedings, and she said, put it in the Cornell Archive preprint library, which I did, so I was grateful for that. But they wouldn't accept the paper because they couldn't get agreement from anyone that it should be published. So that's the translational, but now adding the vortical, anticyclones and cyclones. And this is my equation to calculate that. So this is where I'm coming from. And all these things can be measured. The variation in these other ones doesn't matter that much. Of course, for water, it goes from solid to liquid to gas. So it has a huge variation in the amount of entropy that it has, depending whether it's solid, liquid, or gas. In the gas state, that's when most of the energy is needed to sustain it in its motion. But even more is needed, another order of magnitude is needed to keep it going in an anticyclone or a cyclone. So I think the concept isn't that difficult. So now this is my general model, modified by adding this. I gave this model a couple of years ago here. Didn't have the vortical element included. You know what anticyclones are, you've seen maps of them. Look how Australia, there's a bit of cloud here because air is being drawn up here from the bight, and you have cloud, particularly where you've got interaction between the air cells. And the tropical cyclone, I don't know which one this is, but it looks pretty fierce. The Queenslanders know about it. My good friend up there, John Reganzoni, has been bombarded many times. And all the forests that were planted up there by forest companies were destroyed by cyclones. That was a good tax dodge, but it hasn't led to any real benefit planting those forests to Australia because they didn't take this into account.
That was a pretty extraordinary year. Just go back.
Yeah, if I can. I'm going to go back here.
Because I look at these things the whole time.
Yeah.
And there's this thing called the interactive, whatever it is, where you get them tracking across the continent.
Sure.
What's so unusual about that
Yeah.
is the number of quite intense low pressure systems.
Yeah.
I mean, like there's one on the Queensland New South Wales border,
Yeah.
and then you've got that one there south of the Gulf, and then of course you've got the big boy there. But
Yes.
it's very unusual to see three things like that. You often get one over WA separately off the.
Yeah, well, we're going up into the Ord to do some measurements. It's the dry season. The Ord is here.
Mm.
And Sandalwood company up there has invited to, have offered to give me help to fly the drone. So that should be fun. I think I mentioned my brother's flying up from Perth, so he's looking forward to it too. And really, when you look at that and realise there's all this extra energy in those structures, that's what I'm proposing. I think the whole thing makes a lot more sense. To me, you know, it was a revelation. In fact, I really hadn't. It happened after a period of 4 weeks when my student Lily Perry was murdered in Argentina. Some of you may remember that. She and her sister were murdered by a nephew. Lily only went along, she'd just been promoted to full professor at the University of New England in January. On the 11th, on the night she gave a talk in San Diego, went up to join her sister, and they were murdered the first time they went to his house. He already had the grave prepared. It's just beyond belief. And she was just at that takeoff period for her career. So consequently, I was in a state of mourning, as you can imagine. Students become like extended family. But when I started to think again one morning, this occurred to me. So I don't know if Lily's intervening, but at least the fact that that dreadful thing happened did give me clear mind, you know, to think with, a bit of a clean slate perhaps. I'm probably going too far with that. Of course, water varies very much more as you go with altitude, the parts per million compared to CO2. I don't really want to. The increase in water being applied to land is shown by this map. This is the area, this is up to 2009. So we've had over a doubling since 1960 in the amount of water used in irrigation. There's a linear correlation. How are we going for time? Okay, well, the atmosphere contains about 12,750 cubic kilometres of water. That's enough. If it all rained out, you get an inch of water over the Earth's surface.
Yeah, so much for the graph.
Doesn't seem like a lot, does it? Yeah. An El Nino, La Nina cycle, varies the water in the atmosphere by about 510 cubic kilometres, according to Tremberth. That's his estimation. I reckon the greenhouse effect from water is about 23 degrees of the 33 degrees that the atmosphere warms the Earth. Carbon dioxide is a lot less, of course. So that, just on a simple proportion, that would mean that you get about a 0.9 degree increase globally during an El Nino, which is what's observed. It increases about almost 1 degree lately. The amount of forcing has been estimated by IPCC related labs is at about 4.2 watts per square metre, variation in the El Nino cycle. So my estimate is our irrigation is adding about 100 cubic kilometres of extra water to the Earth's atmosphere over land, and that should give a greenhouse effect of 0.2 of a degree with a forcing of about 1 watt per square metre. So the reason I think that water's been overlooked is that it has such a huge effect, so that even a minor change will make a significant effect. Everyone says when you say it, oh, what about all the sea and all the water out there, you know? But the fact is that water over land, air over land is much drier. So this is an area where we can keep adding water, and I would expect we'd continue to get warming, but it will stop warming when we don't add more water. Or if we get more water efficient, we might be able to reduce it, that effect, if we regard that as important. So I think Wes's volcanoes...
One thing maybe I can just highlight the
Yeah.
importance of turbulence is this submarine volcano of Madagascar.
Sure.
It was responsible for 10 intense tropical cyclones
Yeah.
in the 2018-2019 season of southwestern Indian Ocean.
Yeah. So
And they have all the sustained wind speed and the pressure,
Yeah.
all on the wiki
Yeah.
page.
yeah, well, all that sounds consistent with me. You've got a real witch's brew there. So
Yeah. And we know
of heat
different
and water.
times when these tropical cyclones occur, where the hot patch of seawater is located.
Yeah.
And we can see
Yeah.
the
Well, I
temperature
think
gradient.
we can model that.
Yeah,
Yeah.
I think you should.
Yeah. Okay.
You're the modeler.
So look, the effect of irrigation is pretty small in the whole scheme of things, but the temperature increases we're talking about lately are also pretty small. They're not that great. They're not as high as people had predicted with their models by almost a factor of 10. And the direct sensitivity you have here is 0.23 degrees per watt per square centimetre. And most of the greenhouse models are much higher than that. So what they're saying is that you get a bigger temperature increase from a smaller amount of radiative forcing. I think, again, the Trenberth, the mass of the atmosphere, is my reference there. This is the sort of modelling I'm doing. I use an old-fashioned program generated in the early 1980s, but it's sort of a pure thought program. I don't have to have complicated programming language. I can just think what I want to do and do the calculation. And I can do it very quickly. I can write programs in a couple of days. I'm not going to dwell on this, but I have made another estimate of the amount of warming that you could get from adding water at a particular location from all of the 20th century irrigation. And again, I get about 1 watt per square metre for that. Another of my programs, I've already done that one. What am I doing? Just going back to the El Nino, warm Pacific Ocean, lots of water evaporated, lots of cloud, the atmosphere rises higher because of the water, because when it volatilizes it forces the atmosphere up. Therefore it's colder at the top, therefore you get less radiation to space during an El Nino. I predicted that when I first started thinking about that, and when I looked in the papers involved, that's exactly what happened. There's a very significant decrease in the heat going to space over the Pacific during an El Nino. That's not the case, of course, in Australia, where it's dry and we don't have water under those conditions. But you can see the development during a period here of extra water vapour during an El Nino development at 10 to 12 kilometres. So a lot of extra water is high in the atmosphere. So I see the El Nino as the kind of the model. Again, I'm going to skip over that. And the correlation between the El Nino, when heat is being trapped, over the ocean, and the temperature increase is quite good. Under the La Nina conditions, you've got the opposite. So when you see a peak here, you see a depression here in the outgoing long-wave radiation. So that means more heat is being retained in the Earth's atmosphere. Again, I'm emphasising, I'm talking about short-term, I'm not talking about long-term geological variations. So summing up so far, irrigated areas significantly raise local humidity for months, and I estimate they can trap up to 50 watts per square metre just in that region. That's why I've got the drone to go up there and do some tests. When I told Ian Watterson from CSIRO that I was actually going to do some measurements, he said, well, gee, that'll give you really good credibility, because most climate scientists use data already generated, which they look at in their computers. Of course, the new data is always being generated, so they never run out of a job. But are they getting anywhere? So the radiant surface heat is absorbed in water vapour plumes. The rain out later is irrelevant, as evapotranspiration is continuous, giving 1% more water vapour in air. And this emphasises that the dry areas where irrigation is practiced is where you're going to get the greatest heat trapping in the atmosphere, because it's a logarithmic effect, and the more water you've got in the atmosphere, the less the effect. But if you're doing it in a dry area, you're going to get the strongest effect. And I think that's another reason it's been underestimated. That hasn't been taken into account. The GCMs don't predict what I'm predicting. And I think that's because they're very localised. They just look at the air above the irrigated field rather than looking at the dispersion of the water that must occur very rapidly. I can illustrate that. And the other point is that irrigation is increasing linearly as we grow more food for the human population.
Globally.
So whereas CO2 is increasing in its effect logarithmically, because it's a pure radiation effect. Lake Eyre, I believe, is flooding. We're planning to take the drone out there as well later in the year.
Is the Cooper flooding?
Yes, it is. Oh, I don't know about the Cooper, but certainly the Diamantina. And so on.
It is in the north.
Yeah. And I don't know if it's going to be as big as 1974. 1974 was the biggest ever recorded flooding. It started in January, and flooding started in, I was talking to a mining engineer who was up there. They were planning to put a drill down, but it was a year before they could get back, because their airstrip was completely inundated. I think the windsock was just out of it 6 months later. So I thought that was a graphic.
Is that red coming down into the lake? Is that coming from the Warburton?
I think so, yeah. The Warburton's up here, actually.
Yeah, that's right.
Well, the Warburton comes in through the north.
Yeah, that's right, up there.
Yeah, no, that's it's going to be funny.
Cooper's Creek comes down in midway down
What I did, though, was estimate from data available the greenhouse effect, or the decrease in outgoing long-wave radiation as a result of the 74 flooding. We'll be able to get better data now because satellite data is far more reliable. To a certain extent, in 74 it was estimated, because the first real satellite to measure the atmosphere only went up halfway through 74. So we should be able to improve on that. But this shows that there's a huge decrease in the outgoing long radiation from the flooding of Lake Eyre, comparing 1978, when it was dry again, with 1974. So we can use this approach to actually test these hypotheses. This is subtracting 73 and 78, 2 dry years, to see the variation from one year to the next. And you just don't see that kind of concentrated effect averaged over the whole year for Australia. So that is consistent. Recently I had a paper rejected, largely because the reviewer confused those diagrams.
Oh.
And I'm just about to write the savage responder, just for the record, because I'll write a book about all this later, I think. Assuming I'll live long enough. This is irrigation as practiced in cotton growing. The reason that these fields are picked out so that nearby farmers will know that pesticides are going to be sprayed, or herbicides, and consequently can plan accordingly. But you can see that it's not the whole area, it's just part of the area. So the water will naturally be dispersed, and it'll be dispersed even more by the rotating air masses. So the effect of the added water that's coming from the crops will be increased. If you look at the ice ages, temperature variation, the amount of ice volume going backwards from present, there is a matching with carbon dioxide. There's also a matching with the amount of water that you're going to see in the atmosphere. These are the ice ages, the depressions here. This is the end of the ice age. At the moment we're in such an ending. We'll almost reach the peak of the warming that's occurring according to this thinking.
Let's see how fast it cools.
Water vapour in air varies hugely with the temperature. So you go from minus 10 degrees, there's about 2 grams of water vapour in a kilogram of air, but at 40 degrees there's 50. So that's hugely responsive to the temperature, the amount of water vapour that you can expect to see in air. And consequently, if you've got, what have we got here, about a 5-degree difference, a bit more than that, let's say going from 5 to 10, you can explain most of the Earth's temperature by the water vapour that's in the atmosphere, not the CO2. Now CO2 may have a role in initiating it, I'm not sure of that, but...
Can I ask a question?
Yes.
Can you relate those 3 columns to the amount of carbon dioxide that might be in the atmosphere?
Well, that's known. I just haven't plotted it. So you can relate it, yes. And it has been proposed that carbon dioxide caused the warming, because it goes up as the temperature goes up.
But it lags.
But what you're talking about is the amount of water vapour that
I
is
am.
in the air. And that what you're saying, as far as I understand, the whole gist of this thing is that you're saying the greater the water vapour in the atmosphere, the more carbon dioxide is trapped in the atmosphere. Is that what you were trying to do?
Not really, no. I'm not referring to CO2 in the atmosphere much at all. CO2 will come out of the ocean as it gets warmer, and it will be released.
It's not just CO2. Gases solubility in liquids depends on temperature. The higher the temperature, the lower the solubility.
Yeah.
I learnt that 60 years ago studying gases in molten glass.
Yeah.
But it doesn't matter what the liquid is, it's the same deal.
Yeah.
And the CO2 lags behind the temperature in these ice cores. So it's the temperature rise that's causing the CO2 rise. It's the CO2 coming out of the oceans.
Yeah, certainly that's not a proof that carbon dioxide is the cause that lag.
No,
in fact, my colleague,
the temperature's the cause.
my colleague that's coming from Bosnia is doing harmonic analysis of ice core data. I'll be going to the airport to collect him at 11, and he's got a poster on that. So very much along the lines of what you're saying. And he has been able to calculate the lag. And I've just asked him to recalculate it so we can have the lag in this period when the temperature's falling, and also in this period when it's rising. Obviously the lag is going to be less when it's rising sharply, but can we refine the analysis so we can see if that's 50 years or something like that?
800
Thought it was 800.
That's the conclusion from
Yeah.
people who've done the analysis.
Yeah. So the idea that carbon dioxide was causing that increase in temperature has been pretty thoroughly knocked on the head. I don't take a strong position on it. I just wanted to see what the data actually says, if we can refine that analysis and determine what the lag is.
There are.
But what I am saying, though, is that the main controller of the Earth's temperature is water in the atmosphere. And also, I'm also saying that surface turbulence could be a factor. So if we build cities like China is, all over the place, growing up like mushrooms, Tianjin, where I go all the time, built a city to house 20 million people in 10 years. And they moved everyone out of the old accommodation and they're trying to get them into the new accommodation. A lot of it's empty because it's very expensive. But trade is helping lift their standards of living. I just don't think I'll talk to this. I think I've said enough words. I just want to indicate that I'm doing modelling, what I call regional. I call it action modelling, because I'm using this idea of rotational motion at all scales, from the vibration to the rotation, to the translation to the vortical. The action is what actually determines how much energy is needed in the system to sustain its motion. And I think this is a new approach. This is not the approach being used in the global climate models. They're using, if I can be scornful, 19th century mathematics of fluid motion. And they regard the air as a continuous fluid without any particles in it. I mean, obviously that's not true. We now know there are molecules, but when the mathematics was developed, people didn't know there were molecules. It wasn't until Boltzmann and Einstein came along with his Brownian motion that we could prove that molecules existed. So I'm not going to read out the detail of that. These are some of the modules. I'm coming up with a set of modules. I don't want a whole super module where you link them all together. I just want to be able to calculate the different components separately. There's the insulation at the surface, the reflection. You have to take that into account in your modelling. You have to take the total absorption of sunlight on the surface and in the water vapour. You have to understand the evapotranspiration. An Australian scientist who came from Perth, Penman, initiated that research. Australia is such a dry country, we really couldn't do agriculture without understanding of evapotranspiration. They don't need to understand it in China because there's water everywhere. And the system is more or less at its peak from that point of view. There's conduction, the thermals conducting from the willy willies and so on. That's a minor part. There's the greenhouse absorption and emission. That's the radiation from the surface, minus the outgoing long-wave radiation. That's the greenhouse effect. These are simple equations. The surface radiation from the Stefan-Boltzmann equation, the amount of radiation varies to the 4th power of the temperature. This is something that Boltzmann established. The entropic energy of the atmosphere, that's taking the entropy per molecule and multiplying by the temperature, you get the amount of energy. This is not just the kinetic energy. This is potential energy as well. So the total entropy is the vibration plus the rotation plus the translation plus another component for kinetic energy. Multiply those by temperature and you get the total amount of energy needed to bring the atmosphere from absolute zero to whatever temperature it is. Of course, at absolute zero, if we cool the surface of the Earth down to absolute zero, we won't be moving. But maybe we can live forever in that state. The total atmosphere will collapse to be about twice the height of this room, a solid block. Switch the sun off, and I think after I calculated once, this would take maybe 6 months. That's the way I think, I guess. playing games. And then you heat it up again, it will melt at some stage. The different gases melt at different temperatures, and then it will vaporise. Carbon dioxide vaporises at a lower temperature than water, and it melts also at a lower temperature. So on Mars, that's an important part of their climate. I'm adding now the vortical entropy and energy, and it's the potential energy of angular momentum, and the turbulent release of kinetic and potential energy in the anticyclones. That carries heat from the tropical zone, or the subtropical zone, down through the temperate zones. And then it will actually carry cold north. So if you get these polar vortexes, that's where the cold is coming from. The turbulent release, and then Planck radiation. I've been looking at the basic theory of that too, and writing some programs so I can better understand it. And I think I'm already getting some interesting outcomes. Then there's the partitioning of carbon dioxide between air and water that we've been referring to. I think we need to get a better handle on that if we're really going to understand what is giving the concentration of CO2 in the atmosphere. So I conclude with this thought: what is cause and what is effect? Water vapour is a major controlling influence. What about CO2? Is there similar direct field evidence to support its role? Not as far as I'm aware. I can see the logic of it, but I don't see the experimental evidence that's been obtained in the field. I'm an environmental chemist. We do all our research out in the open. The last couple of days I've been fully occupied answering questions about glyphosate, the herbicide. It's safe to use. It's not carcinogenic. I stake my reputation on it. This is the anti-GM movement.
Exactly.
And they're going to win. It will be banned because, well, companies will stop making it because they can't afford to keep making it because of the court cases. And we'll lose a perfectly good chemical which will be replaced by more dangerous ones.
Exactly.
And more expensive, probably.
More expensive. The chemical companies will do quite well.
That's exactly.
So it's the farmers that suffer. Personally, I'm very much in favour of biological agriculture. A lot of my research has been on using microorganisms, biofertilisers in Vietnam, to reduce the amount of chemical you need to use. So I think this is the rational approach to take. So I don't think we should just have open slather with chemicals. We should be very careful how we use them. And we should never put too much on for the system to absorb. But glyphosate has the simplest structure you could imagine. It's made up of carbon dioxide, ammonia and phosphate linked together. The bonding occurs in thousands of the molecules in our body. If it was carcinogenic, we wouldn't exist.
Exactly.
Can't be carcinogenic. I call this the common sense test. I call it the common sense. Just look at the molecule. You can go onto Wikipedia and look at it. Sorry, this is not much to do with climate change, but in between learning to fly my drone and preparing for this talk, I've given about 7 or 8 interviews, and quite a few of these have become podcasts. I think none of them visual either. So there's only a loose correlation between increasing concentration. the problem with CO2 is it's well mixed, so you can't see any variation. But we do know that in the Antarctic, even though the CO2 is just as high as anywhere else, the temperature is not changing. Is that because there's no water vapour in that atmosphere? That's my suggestion. It's perfectly dry. The Antarctic is a desert. Okay, that's the way to think of it. It has snow and ice on it, but the rate at which snow falls is very small. A lot more. There's a lot more water vapour in the atmosphere in the Arctic. So the jury is still out regarding the magnitude of the role of increasing CO2. I think water may provide a bypass, even provide a bypass for the carbon dioxide forcing. I'll be discussing that. If someone can convince me otherwise, I'll accept it if their logic is impeccable or their evidence. And the vortical heat capacity that I'm proposing should reduce the climate sensitivity to greenhouse gases anyway. So maybe the real cause of temperature variation resides in water variation and also, if you like, the roughness of the Earth's surface. Maybe having nice forests gives a smoother surface with less, and so that more heat can move towards the poles. Just imagine this, you have a whole set of windmills around the globe causing turbulence and causing local heating and stealing heat that should otherwise be going towards the poles. Eddington made the point that we shouldn't use tidal energy in the long term because that will cause the moon to move closer to the Earth, because you're dissipating some of that potential energy.
So I think it's retreating 3 centimetres a year.
Well, it's retreating, is it? Well, maybe that shoots a hole in the... We'll look that one up. But he was certainly against it on that grounds, that you were disturbing a natural process, you were stealing energy, gravitational energy, and consequently that was not a good thing to do. But you had to be a long-term thinker to be worried about that. And I don't think humans have been that worried.
Geologists.
Just continuing the debate, 2 presentations we've got. Big Data I'm going to meet, designing a regional climate model to test the hypothesis that increasing anthropogenic use of water is a contributor to global warming. And Big Dat's presentation, harmonic and time core analysis of Vostok ice core data. We're using a machine learning approach to predicting climate fluctuations. He's from the American University of Sarajevo and the International University. And that's my talk.
Well, I've got to come over this way a bit more, have I? Thank you, Ivan. Again, it's a pleasure to have you along. Questions, anyone? Far be it for me to ask a question on the sciences. I'll leave that to Peter.
Well, it's a simple question. You've been careful to point out that your hypothesis is not relevant to geological timescales, it's short term.
Yeah.
But what time frame do you consider short term?
I guess I'm thinking at the moment in terms of 50 years, you know, during which human activity might make a difference. And I'm just extrapolating from the fact that we can affect climate locally by growing lawns and so on. So what scale does that effect become unimportant as far as the Earth's future is concerned? But as far as I can see, we can affect it, but within testable limits. And how serious it is, whenever I hear a scientist talk about catastrophes, unless they're talking about comets colliding with the Earth, I switch off, because that's not a scientific term. You need to have some sort of quantitative measure if you're predicting some serious result or event. And catastrophe is not shouldn't be part of the vocabulary.
Paul.
Yeah, when you were talking about the effect of irrigation,
yeah,
I imagine that when you irrigate land, that'll lower the surface temperature.
Okay,
I was wondering what impact that might have on radiation.
Yeah, no, that's a good point. India is probably about 1 to 2 degrees cooler at the surface than it would be if they weren't irrigating, and that can be estimated. If you're just talking about irrigating, say, a cotton crop and measuring a temperature difference just above it, it could be 5 degrees cooler where that water is evaporating, particularly from the crop itself. It's a significant cooling effect. So that can affect the local, we call this climate or weather, certainly the local environment anyway. But that heat still exists, and that's being taken up into the atmosphere, and it's released when that water condenses to make clouds or falls as rain. And at that point, it radiates heat. And my hypothesis is that that radiation is what goes into driving this flywheel. It's able to activate it, affected by gravity as well. The gravity is important, so the Coriolis effect. So that heat then, which was taken from the surface and makes life more tolerable if you've got it around your house, is going to end up somewhere else. So it's not, for the modelling, for example, when I'm looking at what heats the atmosphere, you've got direct heating from the sun, absorption mainly by water. So that's at very short wavelengths, because water can absorb at short wavelengths. Then you've got the evapotranspiration from the surface, and those two are about equal on the world average. They're both about 80 watts per square metre. The greenhouse effect itself, that is the absorption by water vapour of radiation from the surface, is about 120 watts per square metre. So the direct absorption and the evapotranspiration is greater than the greenhouse effect from water. So the effect of water is not just a greenhouse effect. So this is heating the atmosphere, getting these flywheels moving, which then through friction pushes the heat back again into the surface layer. So that heat that was absorbed in evaporating the water during irrigation will appear somewhere else. I believe they had very hot temperatures in northern India recently. So maybe that's the frictional heat emerging. I just see this as a logical way to think about these things, and it gives a framework that doesn't exist in the IPCC greenhouse models. That's a game for specialists, not ordinary people like me.
I'm not so sure that Ivan's necessarily an ordinary person. Your science leaves me for dead. I'm going to ask Peter to ask a question in a moment, but listening to your presentation at the end there, you have a presentation to make at Penn State.
It'll be much shorter.
Okay, if that's 2 months, that's only barely 2 months away now.
Yeah, that's right.
Your planned trip to the Ord River is between now and when you depart. So will that complement the observations and the material you pick up? Will that complement your presentation in Penn State?
Well, it will. It will to the extent there'll be photographs of me driving the drone. and if Ian Watterson is right, it'll give me credibility because I'm actually gathering my own data. I've been today. Keen Maisels is the expert who put together the module that is measuring temperature, humidity, altitude, longitude. It's a full GPS, so you get a whole stack of data, and then a reading every second. So we'll be running the drone. The drone can run for half an hour on one battery load, but we won't be running for half an hour. We'll be doing vertical, zooming it up to maybe just 150 metres, because I just want to know how much water is coming off the crops and how much is not coming off the nearby areas where it's not irrigated, because that's the important part of the model. We're guessing otherwise. Well, I think it's about 60% of what's applied, but there's nothing like hard data to prove the point, and it definitely gives you more credibility. So that will be included in the talk. In a way, it's the reason for it, because I was talking to John Runcie, another colleague of mine who's an instrument maker, and he suggested this drone approach. So if you had asked me 5 weeks ago, I would have said you were crazy, or I was crazy to be even considering it. Certainly my wife thinks I'm crazy.
Can I just ask a layman's question?
Sure.
If we could irrigate the Sahara, or indeed Central Australia, and grow crops there and forests and so on, a wonderful concept of green land.
The way it used to be.
In the way it was at one time. The world was different then. But is your hypothesis suggesting that there would be even more significant global warming then?
If we were doing that, I would insist that we should reward water use efficiency. I think we're probably using 2 or 3 times more water than we need to use to grow the world's food. So there would be room to allow the Sahara to bloom in that kind of modelling, provided we rewarded water use efficiency. This is something I've been saying to people. You talk about carbon credits. What about greenhouse credits for water use efficiency? I'm trying to introduce that idea. So that would mean farmers who use less water to grow their crops would get some kind of premium for doing that. So I think we could easily accommodate the Sahara in that.
And the Nullarbor.
Well, yeah, I'm not sure we really want to do this. We can get a lot more efficient growing our food. The Green Revolution and more recently genetic modification is making a big difference. Things like weed control, the weed control at the moment, provided glyphosate isn't banned, is the best it's ever been. And that just means that farmers grow more crop. Some people try to estimate whether GM crops are more productive than non-GM crops, but I don't think it's something you can measure that well, because the amount of pests and adverse conditions are so variable. So you really can't do experiments on that. But farmers are doing the experiment, and they're adopting the GM technology wherever it's been shown to be effective, because they make more money out of it. Monsanto isn't the terrible beast that the world seems to be making out that it was. They had very good scientists, and they came up with very good technology.
Peter, you had a question.
Yeah, I'd like to pose a question on the reliability of climate change models. As you've said, they're GCMs, general circulation models. They're the same models that weather prediction is based upon, right?
Yeah.
Then made more elaborate. Climate change is a hell of a lot more complex than weather. Yet these GCMs, the most accurate forecasts on planet Earth for Cat 8 airports, this is major airports for very good reason.
Yeah.
they have a validity of 12 or 24 hours.
Yeah.
In the 48 years that I've been driving light aeroplanes around this country,
Yeah.
the number of times I've been in Cat A airspace and the forecast has been totally ratchet doesn't give you much confidence. The other thing is that I think I learned years ago is with with mathematical models, the models don't predict the real world, don't put any faith in the models. And these don't. As you've said, they predict temperature rises much faster than the actual. They predict a hot spot over the equator due to the positive feedback thing. So they don't reproduce the real world, right? And you've got something that's much more complex than climate, and climate's not that predictable at any rate. So how much faith can you put on them when they're talking, now they only talk about 400 years ahead, but how much faith can you put on them? I'd say none.
And Judith Curry says that for 30 years in a row, they've predicted twice the warming that's been observed subsequently from 1991.
That's the sort of point I'm making.
Exactly. It's twice, yeah.
Well, I mean, as you can see, I'm dissatisfied with those models, and there's no way I could run them anyway, because you need a huge amount of resources, lots of people. When I was in Asphodel the other day, I was able to sit in on a teleconference in Hobart where there were about 10 oceanographers. And to me, that was a privilege. And they were talking about their computer networks that they've got set up so they can do, for example, they can model all the kinetic energy in the ocean, for example.
Yeah.
And they have to have access to computers all over the nation to do that. There's limited computing ability, but they need these huge resources. I would prefer to break things down into something that's much more manageable and then build up from that. I have respect for these people. I think they're professionals and they're doing the best they can in the circumstances. But there's no way I would even consider getting involved in that, because it'd be a total waste of my time.
Yeah, but I guess what I'm trying to get at is how reliable do you think they are?
Well, I mean, the evidence is they're not able to predict, as you say, beyond a few days. I saw a paper recently from John Abbott that showed that just by using the past, a record from the past, and you could actually make better predictions about what the weather will be next week than you can in the Bureau of Meteorology models. But they're part of a world network where everyone is cooperating with everyone, and they're not really in a position to be able to pull out of that and do something different. But maybe that can be changed. Yeah. But certainly by having regional models and getting a clear understanding of the physical principles involved and making predictions that can be tested, it's almost impossible to make predictions that can be tested using the GCMs. Yeah. Partly because people don't know what's in the models.
It's completely opaque.
Public tested every day.
Black
boxes. We did the weather forecast and then we went complain the next day.
Okay, well, it is testing, but I always said that the best way to predict the weather is to say today it'll be the same as yesterday. And you'll be right 80% of the time.
Paul, you had your hand up there. Not close.
I worked for Tony Abbott on election day, and he lost.
Yeah.
There was two reasons why the locals and others opposed him, but one of the reasons he was opposed so vigorously was he said climate change is crap. Climate change is crap. This is a very short question, really. Are you saying climate change is not crap, but it's not caused by CO2, it's caused by water? Is that what you're saying?
I'm saying that Yes, basically that's what I'm saying. Not only water, but also surface roughness now. Friction.
Yeah.
Now, I've talked to climate model people working in climate science in Canberra about this, and they didn't regard friction as important. But I'm proposing it's really important. It's really what keeps us warm on an annual, yearly, century basis. But the addition of extra water on land, I think, is also increasing the temperature, perhaps as much as CO2 or more. So that's what I'm saying.
Thank you.
So therefore, I would say that a lot of the climate action that's being proposed is not going to solve the problem. So does that mean Tony is right?
I think Tony was referring to human
caused
climate change.
All I can tell you for sure is the after party was not as joyful as it might have been.
Yeah. I hope they have windmills down at Manly now.
Yes.
Well, I voted for it.
Can you just explain to me why, obviously we're seeing some of this ice cap is melting away and great shelves of ice that are floating off into the ocean. Again, is this to do with friction or the world needing more water to cool us down or warm us up? Or what do you feel about that?
Yeah, well, most of that's occurring in the northern hemisphere. It's not. I mean, the sea ice is varying in the Antarctic, but I think the total amount is actually increasing. The sea ice. There might be some diminution in the cap itself. Now, what's going to cause caps to melt? I think it's friction.
Yeah.
So I would say there's more friction in the northern hemisphere because there's more land. And there's more roughness, if you like, on the surface. And well, the polar vortex could be an outcome of that.
You said earlier on that big cities, skyscrapers, or you implied that, were adding to the friction.
Well, I haven't been able to quantify that.
I was going to say, I mean, surely big cities as well don't amount to very much in terms of the Earth's surface.
If you look at China, they amount to a lot. Since I've been going to China, there was one, Hong Kong, and Beijing was never a city of skyscrapers. But flying into Hong Kong and the old airport was quite an experience. Because you almost caught the washing as you went through. But then I noticed that cities were spreading north like a disease in China. And they're everywhere. So
can you quantify that?
Well, I think it's going to cause local heating, and that's where our thermometers are in those cities.
That's right.
Our thermometers are not out in the countryside. Well, there's a few out there, but the majority of them are in cities, and they're also in airports.
Yeah.
Can you imagine a more turbulent place?
Yeah.
Wes, you said that the temperature's going up in Hong Kong's airport at a great rate, even though it was a cool...
1998, we moved the airport at Tai Tak to the new location.
Yeah.
And we've set up a new temperature gauge at the new airport site.
Yeah.
And that location now is one of the hottest places in Hong Kong, especially after sunset.
Well, you could call that an experimental test of my hypothesis.
Yeah. Maybe I should answer the Arctic sea ice question because I've studied this.
Yeah.
Arctic sea ice has been monitored since 1979. And based on the last 10 years record, the lowest sea ice ever was 2012 September. September is a good time to look at the minimum sea ice because after the summer season. The 2012, I think if you refer back to my talk, was El Hierro, a submarine volcanic eruption changing ocean circulation patterns in the North Atlantic. And the sea ice contracted more in the North Atlantic than, say, the Bering Strait. But then in 2014, the North Pacific Bloc, this warm patch of seawater that people misinterpreted as global warming, was the result of a submarine eruption initially south of Tokyo. And this led to the North Pacific Bloc. And the Bering Strait part of the Arctic sea ice contracted much more. In fact, it's consistent with ocean warming in the Northern Hemisphere. So it was published.
And that would also put a lot of extra water into the atmosphere, and that's actually measured. You can the most northernmost temperature measuring place is much warmer in the northern hemisphere, and the humidity is much higher.
High pressure conditions during the North Pacific Bloc. So 2 years in succession, years without winter on the west coast of North America.
When it's flooding over, when water is flooding over land, then you get a lot of evaporation.
You do.
And subsequent transpiration when the plants start growing.
Yeah, that's right.
Like in the Channel country.
Yeah.
Yes.
Up close.
Just a small one. I'm interested in climate change from the point of view, at least it's cleaning the world up in a sense, but I'd have to think about that. Desalination. How is this going to affect what you say? It seems to me that it's growing. If we look at Dubai, even Sydney, but certainly if you're sailing in a little sailboat or cruise boats these days no longer take on water, they have desalinated water. How's that going to affect us? Very kindly.
Well, I don't know the answer to that. The amount of water involved, I guess, is still reasonably small. But the more we do it, and the more of that seawater we put on land, it causes evaporation, evapotranspiration, the more you'll get this effect I'm speaking about. If you use the water in a place that's already humid and moist, it has less effect. If you add the water to dry land, where the atmosphere is already dry, somewhere between, say, 10 to 30% relative humidity, that's where you get the maximum greenhouse effect. Yes. So it's all part of the big equation that we can calculate, actually.
Is irrigation a bad thing in that case, putting more water into the atmosphere? Or should we not irrigate as much?
Heats up the temperature.
The point I was making about irrigation is we need to make it water more efficient, so that we use less water to get the same amount of product. I did write to Pratt, the richest man in Australia, suggested, and earlier they had a program to put irrigation water in pipes made out of waste materials, and I think that was investigated, but no one really supported it in the irrigation industries, so they put it on the shelf. But I think that would be a good idea. It wasn't just, I mean, all this waste plastic can be turned into pipes instead of shipping it off to China.
Yeah, they won't take it.
Yeah, they won't take it. Well, yeah, Indonesia won't take it anymore. Yeah. So you don't actually need just pipes. You can put it in plastic sacks.
Up close, Peter.
So all the irrigation channels could, and we could save a huge amount of evaporation that's occurring from open water surfaces. So my hypothesis has built in a program of work for people to do and for us all to benefit, and I think Lomberg would approve.
Beyond Lomberg, yeah. Peter.
So, thinking about what you were saying in terms of irrigation, it strikes me that irrigation and irrigation channels would have a much larger surface area to water mass ratio than, say, water in a large reservoir. So you're likely to get far less evap from a large reservoir, say, supplying Sydney.
As a percentage.
So are reservoirs that we badly need in Sydney likely to be a problem, or nowhere near as large a problem as, theoretically, as irrigation?
Well, the deeper you make the storage, the less the evaporation per unit of water. The dams that are used in the cotton industry are what they call turkey nests. And effectively what they do is they dig a drain and then heap up a wall inside the drain and then fill up inside, so that the floor of the dam is at ground level. They don't dig it out. So some of those can be kilometres long, some of those dams. So there's a huge amount of evaporation from the surface. So I probably won't be thanked in the cotton industry by suggesting that they put it all in plastic, but nevertheless, that could be a good idea, particularly if they were subsidised to do it.
Well, they do it in tips, so...
Well, I'm mindful of, I guess, one of the biggest irrigation activities in WA. If it weren't for a pipe that runs from Perth to Kalgoorlie, Kalgoorlie and many of the smaller towns nearby wouldn't exist without it. I drove past it, actually fulfilled a lifelong ambition in November, December of last year. I actually drove to Perth across the Nullarbor and back again. And sure enough, there was the pipe there. We were smart enough to do it many years ago. We should be smart enough to renew similar irrigation technologies around Australia. I can see Ivan's busting up to say something here. I have one more question for you, Ivan, and before you respond to that, and that is to, I know it's getting a bit late, but no one's left, so you've all been interested. Ivan's got this presentation to make, as we just learned, in 2 months' time or thereabouts in Penn State. My question, Ivan, is can we tempt you back to give us some feedback as to how your presentation is received in the US, especially at Penn State?
Yeah, well, surely you can. I expect you to come back because it's been very productive for me to come here, and it enables me to pace my activity, really. Because as I mentioned, I no longer lecture at the university. I was retired from that in 2011, and they don't seem to have the same approach to giving big lectures, people, it doesn't happen very often. A few foreigners that come here get the place, but universities have changed.
There's one foreigner that I can think of right now that's up in Brisbane. That's a kidding. Sitting at a high level of
but as far as long pipelines are concerned, well, the Kalgoorlie pipeline in 1949, we travelled from Waroona to training from the dairy country to the wheat belt to re-establish our home, and we went on a Ford A, which broke down in Meckering, not Meckering, Cunderden. My father had to repair it, which he did. The water in town was pretty well boiling because it's in those pipes on the surface in midsummer. But the next morning we went out along the track, pulled up next to the pipeline, and in the morning we all had showers. My father opened up one of the stopcocks. Water went up about 30 feet into the air, and we all took our showers under this stream of water. You couldn't do that now because they've got locks on it, but and of course they have to have those stopcocks to let the air out because you get air, with pressurising pumping. You know about this, the dimension of those pipes. The air keeps coming out, so you've got to release that. So people will be going along, releasing the air locks, otherwise the water wouldn't flow. So that just reminded me of that. But as far as building other pipelines, well, gee, if we can put all our waste plastic into something like that, why not? I mean, you just push this out of a factory, and all the climate concerned people can arrange for it to be installed.
All right, look, we've probably pushed our luck. It's getting on to 10 o'clock.
10 o'clock, as I might add, for those newcomers this evening, is the golden hour. They turn the lights out on us. So we've got about less than 10 minutes to be gone. But look, thanks for everyone for coming. I'll do my little best to, and especially friend over here, John Boone. John kindly added some words into the TWC. Good on you, John.
Yeah, my wife saw it.
And hopefully we'll see you back maybe September sometime when Ivan's back from Penn State University in the US. Thanks for coming.